So again, we are back here. We'll continue with Wien's displacement law. So again, as we are discussing here, see, whenever we receive radiation from the sun, first thing we need to understand, radiation has a wide range of wavelengths. Wavelengths are, and what we see, visible spectrum is a very small part of range of wavelengths which are emitted by sun. And when we come to some term called energy density. What does energy density mean? So different wavelengths. So as radiations are coming, using something like a prism, we can segregate the radiation into several wavelengths. What is wavelength? Okay, there's some energy. So there's wavelength of 400 nanometer, there's wavelength of 410 nanometer, there's wavelength of 450 nanometer. Each wavelength I can calculate. Once the wavelengths are segregated, just imagine through experiment, we can also find out what is the energy contained by radiation of wavelength of 400 nanometer. What is the energy contained by wavelengths of 410 nanometer in that range? So all different wavelengths, I calculate energy and we plot the wavelength against energy corresponding to that wavelength. We'll get some shape. So that gives you distribution of energy across different wavelengths. Energy distribution across different wavelengths. In case of sun, when we plot, this is something like sun here. If this is, what does this graph indicate here? So if this is sun and such as sun is close to 4000 K, if I segregate different wavelengths, what we notice here, see, yes, some energies contained in wavelength of 1500 nanometer. But 1500 nanometer, it contains some amount of energy. Compared to that, as this even more energy, this more energy, we find there's a particular wavelength which contains maximum amount of energy. And what is that wavelength for sun? The wavelength is something like yellowish color. That's why it looks like that. So any object will radiate energy in form of EM radiation, and EM radiation will have different wavelengths. But each wavelength, if we can segregate and plot energy contained by different wavelengths, there's a particular wavelength which will contain maximum fraction of energy. That's called lambda max. So Wien's displacement law. So for what we see in this shape, we see this brown color. Brown color is how the radiation would be if a perfectly black body is heated to 3500 K. I find this is where lambda max occurs here. What is lambda max here? 500, 600, 700. This is something about 800 nanometer. It's lambda max for this radiation. What has happened at 4000 K as the temperature has been reached here? Now I find lambda max has become 700. So, but all other wavelengths are present. 4005 K, it has become something like 650. So each radiation, that's what it is, a perfect black body radiation curve. At different temperature will peak at different wavelengths, and the peak is inversely proportional to temperature. So if I connect all the peak here, it is inversely proportional to temperature. So as the temperature becomes double in Kelvin, the wavelength at which peak occurs will become half. So entire spectrum, as the temperature keeps increasing, keeps shifting towards left. And one more thing is happening here. If you look at a lower temperature, the area is under the spectrum is smaller. As the temperature becomes, area also keeps becoming larger and larger. And this particular region, area under curve is proportional to fourth power of T. That comes from Stephen Boltzmann law. So same object, if I keep hitting at higher and higher temperature, what would happen? The wavelength lambda max will keep decreasing and total area will increase in proportion to T to power 4. So in terms of law, it's very simple. What is lambda max? Lambda max at a particular temperature is equal to B by T, or T into lambda max is a constant, and this constant means constant is equal to 2.9 into 10 to the power minus 3 and SI unit meter Kelvin. That's all. So what does it mean here? And we can understand in different way. So when we observe different star, and of course we can observe color. So the star which looks reddish would be at a lower temperature compared to star which appears orangish. And some star which look bluish kind of thing, which will be even higher temperature. So color of a star is an indication of its temperature. And which is true not only for star, it's true for any other object. And other example you can think of, if we take a piece of metal and if we keep heating it, and if we observe here, we keep a metal and keep heating with the blowtorch or something, first we'll find it will have infrared radiation. And after some time, when it is hot enough, it will start appearing kind of red hot. We raise the temperature in the further, the color will change from red hot to more orange red kind of thing. And we heat it further, it will become like bluish. So what is happening is not the color of the metal is changing. The dominant radiation wavelength is changing. So in case of sun also, this is something like sun. And in the case of sun here, this is something, if I draw a line here, draw a line something like, if I draw a line something around 400 nanometer, 400 nanometer to something like 700 nanometer. This is the part of energy which is radiated, which is falling in visible spectrum. So not entire energy we receive from sun is visible. There's some part of energy which is ultraviolet. There's some form of energy is infrared. And I think typically around 50% of total radiation of sun falls into visible spectrum. And lambda max is equal to 550. Around 550. Based on that, we can find its temperature. And a similar way, you take example of firewood or something like, yes, if you burn a fire, we burn a piece of wood. Typically, it has a temperature of 1500, even a smaller temperature. And when it is 1500, yes, it also emits radiation, but 98% of radiation, roughly, is composed of wavelengths which are longer than 1000 nanometer. And what is the we can see only visual spectrum is something in the 400 to 700 nanometer. So about 98% of radiation emitted by firewood falls into non-visible spectrum. We can't see that. It's only a small fraction of wavelength, which is near to 700 nanometer, which is we can observe. So if we can think of efficiency of firewood for generation of purpose of heat, so whatever energy it consumes and it radiates, only 2% of this, or even less, much less than 2% only is in form of visible light. And that's what used to happen in case of incandescent bulb. Even the bulb also, you notice that the bulb also will have kind of filament. Filament is piece of metal. And so, but when you switch the bulb on, some older version of the bulb, what would happen is temperature will keep rising. As the temperature keeps rising, at lower temperature, yes, similar to suppose the temperature goes to something like 5000 K. If it becomes 5000 K, about half of its radiation, heat is consuming heat energy, it is consuming electrical energy. Electrical energy gets converted into heat energy, which heats up the filament. If filament reaches a temperature of 5000 K, about 50% of the radiation will be useful for us in terms of visible light. So 50% of the energy which is radiated only is useful for light. Whereas these days LED bulb and all, we can control. They are not like the black body. LED bulb and other advanced bulbs which have come, they emit radiation waves which are only falling in visible spectrum, no wastage. Okay, so that is something more of I'm just giving you, and area under curve is proportional to T to power 4. So in terms of questions, they are very simple. Question on B Wiens displacement was only this equation. Lambda into T is equal to constant is equal to this. But this is more in terms of understanding. So any question which comes of understanding, this is what you can understand. And one more last point I'll indicate here. So this is something from here, suppose for, this is for sun of 5000. And let's say this here is, what is the lambda max? Lambda max is equal to 550 nanometer. So 550 meter maximum energy it contains. So any one particular wavelength we pick up, which wavelength it contains maximum energy? 550. Now, if I go to another side here, 550, I move by delta lambda. So this is 600 nanometer. And I move this other side also. This will be, yeah, so this is 600 nanometer. I come to 600 nanometer. And other side, I come to 500 nanometer. Will these two contain equal energy? What we notice here, this side, left-hand side is more steep, right side is flat. So energy contained in wavelength of 600 nanometer will be higher than energy contained in wavelength equal to 550, though they are equidistant from the lambda max. Because here the curve is, it falls steeply, it falls slowly. So I have seen only in the past one question which had come in JEE in advanced once was based on understanding of nature of curve here. I hope this point is clear. This is where maximum is. If we go towards higher side and lower side by equal delta lambda, this will have smaller drop, this will have greater drop in energy. So this will have higher energy compared to this. So that's all in terms of Wien's displacement law. Now coming to kinetic theory of gases, there are only 3-4 points to be understood in terms of kinetic theory of gases. What are the common points we need to understand here? Assumption is, yes, they are moving in the random direction. Size of molecule is much smaller than average separation. And because size separation is large, intermolecular forces are negligible. Thus, E also is negligible. That's why they're separated. When they are in the liquid form, we briefly discussed in case of liquid and solid. Briefly, a liquid solid, there is a strong force of attraction, and small force of attraction leads to negative potential energy. So that's why whatever negative potential energy a liquid has, we need to supply that energy equal to negative potential energy, which is also like binding energy. That much energy need to be supplied to convert liquid into vapor form. And when it comes into vapor form, the separation between molecules is large enough, we can take potential energy to be negligible. So total energy, first key point in kinetic theory of gases, potential energy is negligible. So total energy is only in form of kinetic energy. So what is kinetic energy in that case? And then second thing, what we do in case of kinetic theory of gases, we calculate pressure using laws of motion. So every time molecule, there's a collision taking place, and based on the collision which are happening, if I calculate pressure, we get this kind of expression, and we find the pressure comes proportional to Vrms square. So I'll come to a little more of this. The derivation, I don't think there's a point in going through derivation, but some simple things we'll just discuss about this. So the pressure is equal to this, and we come to some other form also. Here we come across term equal to Rms velocity. So let's understand what does Rms velocity mean. Different molecules travel with different speed, wide range of velocity, and velocity. If we plot number of molecules traveling with different velocity, what we notice, what this curve indicate? This is increasing velocity. So if this is called Maxwell distribution of velocity. So if I take this particular velocity, this is the number of molecules or fraction of molecules traveling this speed. At very high velocity also, there are very small fraction of molecules which are traveling at a speed much higher than mean velocity. So I find they are greater fraction, greater fraction, greater fraction. And this is the find, this is the this particular velocity. Maximum fraction of molecules are traveling at this velocity. Since the fraction is maximum, this velocity, if we think which velocity is most probable velocity, most probable velocity is which has maximum fraction, and that's called. So the most probable velocity comes from the definition of probability and the distribution. This is most probable velocity. And what is RMS velocity? RMS velocity is what is the common velocity all molecules should travel so that the kinetic energy is equal to kinetic energy of molecules traveling with different velocity. So what is Vrms? Very simple formula, and that's what we need to remember in mind. Vrms is equal to 3RT by M. You have come across this formula multiple times, and M is the molar mass, M into Na, molecule of each mass into Na. So this very simple Vrms formula, and this Maxwell distribution. And if you remember the graph, what we notice, among these three, we are talking about three things: most probable velocity, average velocity is whether we take the sum average velocity and RMS velocity. Most probable velocity, this is number 2 here. This is number 3 here in case of RMS, and V average falls in between. Multiple here is between 2 and 3, and which is 8 by pi. 8 by pi is greater than 2, but less than 3. So these are three values, and if you relate, it becomes slightly easy to understand. This is 2 2 RT by M, this is 3 RT by M, this is 8 by pi RT by M. This is the order. And we cannot calculate here. Okay. And that's in terms of the law of equipartition of energy also. So if we talk of kinetic energy, average kinetic energy of a molecule, if we talk of average translation kinetic energy is equal to 3 by 2 dt. Okay. So let's look at what a simple application of the same. Some simple question which have come, and in terms of formula, this is the only thing now. We'll come to a little more in terms of derivation later. So the ideal gas occupies a volume of so and so, and the pressure is this. Pressure is given, volume is given. What is the energy of the gas? Okay. So energy of the gas, how do I calculate energy of the gas? Energy of the gas is equal to, if I take in this case, they not mention what is the, and this actual question which had come, they not mention which form of energy. Of course, potential energy is 0. And when we talk of kinetic energy will have two forms. It will have translation kinetic energy and it will have rotational kinetic energy. And rotational kinetic energy, this year, I think all of you done in chemistry also. Rotational kinetic energy, monatomic particle will not have any rotational component. It will have only translation. So in this case, since it is nothing is mentioned, I'll assume everything is only in case of translation kinetic energy. So what is translation kinetic energy? Translation kinetic energy 3 by 2 nRT or 10 volts. And 3 by 2 nRT is nothing but 3 by 2 PV. So pressure is given, volume is given. It was very simple question. This is the total kinetic energy. So what does this term indicate? 3 by 2 PV. This indicates sum of kinetic energy of all molecules which are traveling at different velocity. Okay. Now come to this question. This question, I have taken up this question so that we understand basis for a little bit of derivation. How do we arrive at kinetic theory of gases? Ideal gas is a temperature T. What is the average force a molecule applies on the wall of a closed container? So if we assume average force is proportional to T to power Q, what is the value of Q? That's what was asked in one of the examinations, one of the questions. We are talking about average force by a molecule. Okay. So let's try and understand how do we calculate average force. Average force is exerted because of what? So let's say if I want to calculate average force on a surface like this. If I want to calculate on this surface, what is the surface? The surface x is equal to constant. Surface is parallel to z axis. So if molecule is traveling and this is surface here, molecule mass is m. When it collides, it exerts this, undergoes change in momentum. And so we know what we need to calculate here. So can we calculate what is the force one molecule exerts? So average force exerted by a collision will be equal to change in momentum in 1 second. That is easy. I think that's what it should come to our mind. Average force equal to change in momentum in 1 second. Now the question is, what is change in momentum in 1 second? So change in momentum, it will happen if we take a plane which is perpendicular to x-axis. Only the x component of velocity will change. So change in x component of momentum due to each collision into number of collisions in a second. That's the force here. So 2-3 things if you want to understand derivation. Average force exerted by each molecule is equal to its change in momentum in 1 second. Change in momentum is equal to is only change in x component of momentum in each collision multiplied by number of collisions in a second. Okay, now let's see what is change in momentum. Change in momentum, each collision is termed into 2m into vx, elastic collision. Now the question is, how do I calculate number of collisions in a second? See, every time if I take this dimension as Lx, it will have collision. After collision, it has to, in x direction, it has to travel a distance of 2Lx. So every time, what is the distance it travels between two successive collisions? Distance is travels in two successive collisions is 2Lx. Twice the x dimension. That's the distance it has to travel in between two successive collisions. So how many collisions it will have in a second? How would I calculate number of collisions in a second? See, it travels a distance vx in a second. So suppose I travel, it travels a distance of vx is equal to 300 meters per second. And if x dimension of the cube is 1 meter, so it means every time it has to travel a distance of delta x is equal to 2 meters for every 2 meters it will have one collision. which is 2 into Lx. What is the number of collisions? V divided by 2 into Lx. That's the number of collisions it will have in 1 second. So this becomes the force exerted by each molecule. And what is Vx equal to? Vx is equal to, see, all three dimensions on an average, x component, y component, z component, all are equal. This x component is equal to V by root. That's the force exerted by each molecule. So, okay, so what we find here, force exerted by each molecule is proportional to Vx square, is proportional to V square, but V is proportional to T. Hence, force exerted by each molecule is proportional to temperature, as Q is equal to 1. So what I have done indirectly, I have done a kind of quick derivation. Yes, Vignesh?
So here, are we concerned with only one wall, sir? Because once it
Yes,
travels the
when we
distance
talk
Lx,
about pressure, are we not considering one wall only? Same thing will repeat. If I have to do what we need to do, if I have to calculate force on wall which is perpendicular to y-axis, I'll replace x component and v component with y components.
okay.
So this is something is the essence of derivation of kinetic theory of gases. Kinetic theory of gases, we treat each molecule like a particle. And similar to laws of motion, the way we calculate force exerted by when number of particles strike on a surface, the way we calculate force, similar way if we calculate force, this is how it will come to. And I hope this part is understood, and it's better if this is understood. Any variation which comes, we can solve like this. And if a total number of molecules present are n, if I multiply by n, it becomes force. And if I divide by area, it becomes pressure. That's how the derivation is. Okay. Now there's one more thing which is called mean free path and mean time between successive collision. Let's understand that part also. Even that part, of course, you can do in terms of formula. But second part is understanding the formula as well. Let's understand. See what we assume here when the collision is taking place. We consider relative motion. In case of even kinematics, also some question, when two objects are moving, if we take relative velocity, because things become easier. So here also what we assume this particle, one molecule is moving, and we take all other particles at rest. Okay, so consider molecule moving with velocity, some velocity which is v relative, ideally v relative, and considering others at rest. And what is this calculation here? This calculation is not easy and we don't bother. We assume, yes, there's a particular, we can pick a frame of reference, we consider motion of only one particle and assume all to be at rest. Or we can also assume this particle is at rest, all are moving at a constant velocity. So let's assume that one is in motion and we have taken relative velocity similar to what you do in kinematics. And it is moving in some V average here. The rest all at rest. Okay. So, and of course, this velocity, with square of this velocity will be proportional to temperature. So in time t, this molecule, which is in particular motion, in a direction in V average. And what is the distance it will travel? Is simple. It is valuing this is a distance it will travel. So in a second, it travels, we start from here. It travels a distance equal to V average into t. That's the distance it travels. Now the question comes, during this travel in delta t, how many collisions it will have? See, if another molecule which is far away, it will not collide with. It will collide with only certain other molecules. Which other molecules it will collide with? See, this molecule which is lying here, it will collide with. What is the condition necessary for collision to take place? If I take the path of motion of this molecule, this the line across this molecule is moving. All other molecules which have their center being at a distance of 2r or less, all molecules which lie within a distance of 2r from the line of motion will collide. Anything more than 2r will not collide. So that's it. It will collide with all molecules which have center within a distance of 2r. So if I make one more approximation, since the dimension not relevant, if I imagine all other molecules look to like to a point mass, so all the molecules which are present within a cylinder of length equal to V delta T and radius equal to twice R. So all molecules which are present in the volume, this moving molecule sweeps in time delta T will collide. So number of collision will be equal to number of molecules present within the volume enclosed by a coaxial cylinder of radius 2r. You understand why we have taken the radius 2r? Because only those molecules which are present with the perpendicular distance 2r will collide. And what is the length of the cylinder? Length of the cylinder is the distance moved. So if I imagine this volume of cylinder, all molecules which are present within the volume of cylinder will undergo collision. Okay, so what is this volume here? The volume swept by single molecule time delta T. Volume will equal to pi d square section area into V average into dt. So this is now volume it sweeps. All molecules which are present in this volume will collide. So if there is the number of molecules per unit volume, and how do you arrive at number of molecules per unit volume? If I do number of moles present in a volume, number of moles into, I've got a number. That's the total number of molecules divided by volume. It gives you like a population density. So this is a number of molecules. The way we talk of India also, what is the population density, population per unit area, and similar way. So we understand here, if population density is more, if there are more molecules per unit volume, number of collisions will be more. If population density of molecules is less, number of collisions will be less. So we are calculating here what is the number of molecules per unit volume, and this number, and let me call this number as capital N. So if that is number of molecules per, so how many molecules will be present in this volume? The number of molecules present in this volume will be equal to population density multiplied by volume. And into this volume becomes number of collisions. All molecules are present within this volume delta V. Number of molecules present will be equal to number of collisions. So this many collisions happening here per unit time. I have divided by delta T. So number of collisions per unit time is this number. This number. And you can look at this, very easy to look at the number. If this is total number of collisions happening in unit time, what is the mean time between successive collision? If I say in 1 second, there are 10 to the power more 4 collision. If there are 10,000 collision, it means average time between two successive collision is inverse of that. So mean time between successive collision is inverse of number of collisions in a second. That becomes the mean time between successive collision. So there it could be number of collisions is one term. Inverse of that becomes mean time between successive collision. And third term, what is the average distance between successive collision, which is also called mean free path. How much distance will travel before it collides? So if time for collision is tau, it is traveling velocity v average. Distance it will travel, we put pi into tau into v average. So this whole term I multiply by v average. This is the mean distance. 1/2 into pi d square. D is what? D is comes from the dimension of the molecule. So when for a given gas, the dimension is not changing. So, and this is something what we have done. We have taken average velocity. And if you do more rigorous mathematical calculation, this comes equal to, if you apply correction for that, actual the number comes to 1/2 root 2 and into d square. This is the mean distance between successive collision. So in terms of, I think, understanding derivation, I think it's not very easy, but not too tough also. And questions which come, it could be any of these three. So one way, of course, is you can memorize the formula, which is the easiest way. And second way, okay, but there's something if you understand is much better. And if you understand, I personally feel we can arrive once we understand this volume. What is the volume it sweeps in unit time? This is the volume it will sweep in unit time. The rest of things we can easily calculate. We arrive at. So if you understand, no need to memorize. But let's look at what the questions which have come. So what is the key point I understood as far as mean distance is concerned? Mean distance between successive collision is proportional to what? It is proportional to 1/n here. You see, as the parameters changes, if I change pressure, what will happen? If I change pressure, what will happen? N will change. D is the diameter of gas molecule will not change. So if we change any parameter of the gas, this number of molecules per unit volume will change. So I just understand average distance between successive collision is inversely proportional to molecular density. It is inversely proportional to molecular density. What is molecular density? Number of molecules per unit volume. That's all I'll keep in mind. Let's look at some questions now based on kinetic gases. Ideal what is given here? Gas is enclosed in a cylinder. The pressure is given. temperature is given. And mean time between two successive collisions is given. So mean time between successive collisions is given. So tau is given here. Pressure is doubled and temperature also is increased to 500. Pressure has been doubled and temperature also has changed. What will be the new mean time between successive collisions? How would you calculate mean time between successive collisions? So this is based on proportionality. So whenever parameters changes, we need to express tau in terms of given parameters. What I keep in mind, mean distance between successive collision. Mean distance is proportional to 1 by n. And what is mean time proportional to? How is proportional to? There's another, because this is something we arrive at mean distance by multiplying tau by b. So tau is proportional to 1 by nv. That's all we need to keep in mind. And what is n here? What is n proportional to? N is proportional to number of moles divided by volume. It is proportional to number of moles by volume, and B is proportional to root P. So I have just expressed N in terms of volume and B in terms of temperature. Why we have done so? Because this is something we finally, I want to get an expression which is in how in proportion of pressure and temperature. I start with this, and here's the population density, number of moles divided by B. Once I write this one, it becomes a little easier. What I notice now, I can use ideal gas equation, PV is equal to nRT, to get a relationship between time and pressure and temperature. Those are two things which are varied here. Can I get this expression quite easily here? It should not be too difficult. V by N is proportional to T by P. So V by N is proportional to T by P. I write this expression. I find it is proportional to root T by P. Now it's fairly simple. How it is double, temperature is increased, I substitute the values, I easily get my answer. Okay, so basically handling the proportion. Another point in kinetic theory of gases is about what is internal energy of gas. See, when we talk about internal energy of gas, it typically is something like mechanical energy. Mechanical energy typically includes potential energy plus kinetic energy. In case of gas, there's no potential energy. So when we talk about internal energy of gas, it is nothing but kinetic energy. And kinetic energy can have two forms. It can have translation kinetic energy and rotational kinetic energy. And when we talk about internal energy is sum of all forms of kinetic energy. Okay. And internal energy is how do we calculate kinetic energy? If I take all molecules, kinetic energy is sum of, when I'm talking first of translation kinetic energy. So kinetic is 1 by 2 mv square. Add it up for all molecules. This will be my total internal energy only due to translation. Okay. And if I use the concept of RMS velocity, in case of RMS velocity, I assume all of them are traveling with VRMS. Okay. So when I equate, so if n is the total number of molecules, n into 1 by 2 VRMS square, that's the relationship. It gives me VRMS definition. VRMS definition comes from here. And RMS means what? How do we arrive VRMS here? To arrive at VRMS here, first we square all the velocity. We have done something in case of AC current also. So if velocities are given like 2, 5, 7, 9, if these are velocities of 4 different molecules, what will be the VRMS velocity? We will go in the reverse order. First we square it and take the mean. Square, mean and root. Square is what? 2 square plus 5 square plus 7 square plus 9 square. If I divide by total of molecules, it becomes mean. And if it is a square root, that becomes my VRMS. So this is a way to calculate VRMS velocity. Individual velocities are given. Okay, imaginary common velocity. And when we calculate total energy, what is law of equipartition energy says, and this is something people have done a number of times, so I will not spend too much of time. So in case of monatomic gas, it cannot have rotational energy. It has what is the law of energy is equally shared in all independent energy states. We call degree of freedom. So a monatomic gas, it can have only translation energy. Diatomic gas, something like this. Diatomic gas can have rotational energy along y-axis, z-axis. It cannot have rotational energy along x-axis because x-axis, what is x-axis here? Along the line joining two atoms which are part of diatomic molecule. Along the line joining those two, along its own axis, moment of inertia is negligible. And hence it has only two rotational energy, 2 degree of freedom. So along two axis, which is perpendicular to the axis joining two atoms which are part of the molecule. So total degree of freedom becomes 5, atomic becomes 6. This is 3 plus 0, this is 3 plus 2, and this is 3 plus 3. And based on that, we arrive at internal energy, and we'll come to this part later. So basically, the CB and CP. This term, I think, no need to revise this part here. So let's look at some simple application of kinetic theory of gases. Kinetic theory of gases is nothing but energy, calculation of energy and ideal gas equation. Okay. Temperature of open room. We have open room, any classroom kind of thing or any other room. It is this volume. If a temperature changes due to sunshine, will the number of molecules present inside the room, will that change? If Ni and Ni and Nf are number of molecules before and after the heating, what is Ni and Nf be equal to? That's what they have asked. This was the question. How do we solve? Very simple. All are anything related to this ideal gas equation, based on ideal gas equation. P is equal to NRT. So in this case, volume has remained changed. What has changed here? Volume has remained not changed here. And what has changed here? The value of N you can easily find out. Okay. So what is Ni and Nf be equal to? I can find out how many moles initially, how many moles of gas initially present. Gas number of moles is equal to PV by RT. Initial value of volume is given. Temperature is given. Pressure is given. Pressure in the room remains same. So pressure is common, volume is common, R is common. Only thing changing is T. So I calculate initial number of moles, final number of moles, PV by R, 1 by Ti is whole thing is initial number of moles. Final temperature, final number of moles. I multiply by Avogadro number. This gives you total number of molecules. So this is as simple substitution. Rest all is simple. Okay, the next question is something like this. If you have an evacuated flask, and in this evacuated flask, if we transfer 2 grams of a gas, it is kept at 25 degrees centigrade. It is temperature T is 25 degrees centigrade. And when when it's evacuated, it will not have any pressure. Moment we transfer gas molecules, yes, it will have experience pressure. Because these molecules have a velocity which are available because of this temperature, and it collides with the wall, it creates a pressure. So this it creates some pressure initially is found to have, this creates a pressure equal to 1 atmospheric pressure. Now, if we add 3 grams of another gas, the pressure becomes 1.5 atmospheric pressure. Because why the pressure has changed? Earlier molecules was because the first gas, now introduce some more other gas molecules. Now there are black molecules as well as red molecules, and pressure created by each gas is independent of other. Presence of other molecules does not change the rate of collision of first gas. So which is something like law of partial pressure. If two gases are present in a given volume, the resultant pressure is equal to sum of pressure if only first gas was present and only the second gas was present. So what does this mean here? If I introduce 3 grams of other gas, if first gas was not there, the second gas would have created a pressure equal to 0.5 atmospheric pressure. Okay, so that's something just to understand also what is kinetic theory of succession. So partial pressure exerted by two gases together is equal to sum of pressure exerted independently. And what is the pressure due to first gas is P, and pressure due to second gas is 0.5 P. That's why total becomes 1.5. And what is pressure proportional to here? Pressure is equal to RT by V. Okay, so which thing is changing here? Where temperature is not changing, V is not changing, R is not changing. First gas and second gas, pressure is normally directly proportional to number of moles. First case, this also, And how do we calculate number of moles? First case number of moles is 2 grams divided by MA. So this P is proportional to 2 divided by MA. 0.5 EP is proportional to how do we calculate number of moles? Mass of the sample divided by MB. What is this one? Molar mass of the second gas. Once we have this ratio, we can easily find ratio of molecular weight of two gases. One last question on ideal gas. Okay, I think almost done. So I'll stop here. I'll continue a little bit from here next session. And maybe I think you can do this question. They're fairly straightforward questions. And we'll